right, it's just past 7:30, so we might get going. Before we start, I would like to say that Women in Nuclear Australia acknowledges the traditional custodians of country throughout Australia and their connections to land, sea and community. We pay our respects to their elders, past, present, and extend that respect to all Aboriginal and Torres Strait Islander peoples joining us today. So, good evening, everybody, and welcome to tonight's webinar, What About Waste? My name is Jazz, and I'm the President of WIN Australia. Women in Nuclear Australia Incorporated is extremely excited to be able to share this webinar with you today. In case you're not familiar with WIN Australia, we are a not-for-profit association of women and individuals of other genders who work professionally in various fields of nuclear technology and radiological applications in Australia. One of the aims of WIN Australia is to promote understanding and public awareness of the benefits of peaceful nuclear and radiological applications, especially amongst women and young people. WIN is an international organisation with members from over 100 countries. We are run by a volunteer committee and would not be able to provide content for our members and the public without the support of our fantastic sponsors. We'd like to thank the Australian Nuclear Science and Technology Organisation, Cyclotech, Gamma Gurus, Global Medical Solutions Australia and Radtronics for supporting WIN Australia and our event this evening. Before I introduce our keynote speaker, I have a bit of housekeeping for us. This webinar will be recorded and will be shared for those that couldn't make it today. We cannot see or hear you, so there's no need to be concerned from your end. You will, however, be able to ask questions at any time utilising the Q&A function at the bottom of your screen. During the panel discussion, I'll pose your questions to the panel. Please remember to be kind and respectful to our guests, as this webinar is designed to be enjoyable by all. Now, let's get to tonight's webinar. We'll start with a presentation by Dr. Jessica Veliscek-Carolan and then be followed by a Q&A panel session where Jess will be joined by Cecilia Tran and Jim Scott, who will answer your burning questions. So I want to introduce you to a WIN Australia member. She said, if just 5 chemical elements could be removed from nuclear waste and recycled, the lifetime of the remaining waste could be reduced from 130,000 to just 300 years, dramatically reducing the hazards associated with nuclear waste to both people and the environment. In addition, these recycled elements can be reused as nuclear fuel, closing the loop of the nuclear fuel cycle and improving the sustainability of nuclear technology. Jessica researches new and stable materials that could be used to treat nuclear wastes by selectively removing these 5 elements. Such materials also have potential applications in mining and wastewater cleanup. Jessica is a nuclear chemist at ANSTO, where she has worked since 2008. She holds a Bachelor of Advanced Science with honours and a PhD from the University of Sydney. In addition to her current work on nuclear fuel cycle, she has worked at ANSTO in diverse areas such as minerals processing and environmental research, and undertaken some interesting tasks, including collecting sewerage and making worm pasta. Jessica has received multiple awards, allowing her to travel all over the world. She was awarded the United Uranium Scholarship in 2011, enabling her to travel and work at the CNEA in Argentina for 3 months. She's also received funding to present at conferences across Australia, France, Mexico, and to attend the 2014 Sharon School and the 2016 Hope Meeting with Nobel laureates in Japan. I'm super excited to hear about Jess's research, which I'm sure you are too. So Jess, I will hand the webinar over to you.
Thanks, Jazz, for your very kind introduction. I will start sharing my screen. To the start of it. Alrighty. Yeah, so welcome everyone. Thank you for coming. I'm here to talk to you about what about the waste and recycling of used nuclear fuel. So Jazz just gave me a very kind introduction, so I can probably skip over most of this kind of background on me pretty quickly, but I did a Bachelor of Science with honours at the University of Sydney, and I did my honours in organic chemistry. So synthesizing organic molecules, but I wasn't sure if I wanted to commit the next 3.5 years of my life to making organic molecules. So I just instead started a job at ANSTO in 2008 as part of the graduate program, which was really great because it meant that I got to spend time in different parts of ANSTO and try a whole bunch of different jobs and see what I enjoyed. So as Jez mentioned, I did some weird things like collecting seaweed from sewage outfalls, like you can see in this photo, as part of the environmental monitoring program at ANSTO. I also worked in one of the commercial units, ANSTO Minerals, and various other things before ending up in the nuclear fuel cycle research group, which is where I am now. And once I found an area that I realized I really liked, which was still in chemistry, but I guess a little bit of all the different types of chemistry, then I decided that to commit to doing my PhD. So I did my PhD part-time while I was still working at ANSTO from 2011 to 2016. And the topic of my PhD was materials for selective separations at the back end of the nuclear fuel cycle. So pretty similar to what I'm going to be talking to you about today, and to my current area of research as well, which I've continued with. So to start, what is the nuclear fuel cycle? So there are two versions of the nuclear fuel cycle, the open and the closed nuclear fuel cycle. Both of them start with the mining and milling of uranium, which is then enriched and used to make nuclear fuel. The fuel then goes into a nuclear reactor, be it a power reactor or a research reactor like the one that we have at ANSTO. And once that fuel can no longer sustain a fission reaction, then it becomes what I've called here used fuel, but what has lots of different names actually. So it might get called nuclear waste or radioactive waste. It might get called spent fuel, or it might get called used fuel. They're all names for the same thing really, but it just depends on your point of view of it. So I will in this talk be referring to it as used fuel because we're talking about material that can potentially be reused. So I wouldn't refer to it as spent because it can still be used again. And I wouldn't necessarily call it waste because, again, some of it can be recycled. So once we hit this point where we've got to the used fuel, it's when we split into our open and closed fuel cycles. So in the open fuel cycle, the used fuel goes to storage and eventual disposal, and it's a once through open cycle. Whereas with the closed fuel cycle, the used fuel is reprocessed. The actinide elements like uranium are recovered and made back into fuel, and we can go round and round in this closed loop, hence the closed nuclear fuel cycle. So there are advantages and disadvantages to both the open and the closed nuclear fuel cycles. I'm going to be focusing today on the closed nuclear fuel cycle because I'm talking about recycling actinide elements that are in used fuel. So I will be talking a lot about the advantages of the closed nuclear fuel cycle, but of course there are advantages to the open fuel cycle as well. For example, the fact that there's less handling of the active used fuel. Also interesting to note that different countries have different policies on open versus closed fuel cycles. So for example, in France, they do reprocess a lot of their fuel and they have mostly a closed fuel cycle. In the US, their policy is to have an open nuclear fuel cycle, but a lot of countries actually haven't really made a decision about what they're going to do with their used fuel. They've got it in short-term storage and they're waiting to see how technology develops before they decide whether they want to eventually go towards an open fuel cycle and deep geological disposal or a closed fuel cycle. So if we are going to be talking about a closed fuel cycle, which are the elements that we want to separate out? So this is the periodic table of all the elements that exist in the universe. And every single element in the periodic table from zinc all the way up to the lanthanides here is present in used nuclear fuel. There are a lot of elements in there. It's a very complex environment in used nuclear fuel. There's a lot of fission products. But the ones that we are the most interested in are these actinide elements, which are at the bottom of the periodic table. They're all the radioactive elements. Some of them you'll probably recognize, things like uranium and plutonium in black. And the other ones that I'm going to be talking a lot about today are the ones in purple, which are referred to as the minor actinides, which include neptunium, americium, and curium. Minor actinides because there's less of them that forms. The other elements that I'll be talking about today are the lanthanide elements, which are just above the actinides in the periodic table, and they're important because they're very chemically similar to those three minor actinide elements that I just talked about. So I'm going to explain more about that later. And why do we actually want to, what are the advantages of recycling or separation and recycling of used nuclear fuel? Well, as you can see from this chart, the vast majority of used nuclear fuel is still uranium. 94 to 96% of used nuclear fuel is still uranium. So if we could separate out and recycle the uranium as well as the plutonium and the minor actinides, then the volume of waste that would be remaining, just the fission products, would be vastly reduced. So the volume of waste that still requires storage and long-term disposal would be vastly reduced, which has obvious cost and safety benefits. As well as the decrease in volume, removing the uranium, plutonium, and minor actinides can reduce the radiotoxicity and the lifetime of used nuclear fuel. So if we look at this figure here, the dotted black line along the middle represents the radiotoxicity, or the how toxic and hazardous the naturally occurring uranium is. So sometimes when people refer to the lifetime of radioactive wastes, they say, you know, it lasts for millions of years, which is true, but it's not really an accurate or a useful way of thinking about how long it lasts, because there is naturally occurring uranium in our environment, in the Earth's crust, in rocks, in the bricks that we build things with, and it is radiotoxic to a certain extent. So it makes more sense to compare the radiotoxicity of used nuclear fuel or nuclear waste to the radiotoxicity of naturally occurring uranium that is already in our environment. So the amount of time that it would take for typical used nuclear fuel without any treatment at all to decay back to the radiotoxicity level of naturally occurring uranium is about 130,000 years. And if we were able to completely remove all of those 5 elements, uranium, plutonium, and the 3 minor actinides from used nuclear fuel, then the amount of time that it would take for the remaining waste, so just the fission products, to decay to the radiotoxicity level of naturally occurring uranium is decreased to about 207 years. So that's a really strong motivation for undertaking this kind of recycling. And as well as that, we're making more complete use of the actinide elements, the uranium, plutonium, and minor actinides, by burning them again as fuel and getting more energy out of them. So to a certain extent, recycling of used nuclear fuel is already done commercially in other countries like France and Japan. And this is the most common process is this process called PUREX, which stands for plutonium and uranium extraction, which, as the name suggests, involves the separation and recycling of plutonium and uranium. So this is a process that's called solvent extraction, which is a liquid-liquid extraction. And basically, you have 2 liquids, one of which is oil-based and one of which is water-based. So how it works in the PUREX process is that used nuclear fuel is dissolved in nitric acid, which is a water-based liquid, and it's then put in contact with an organic solvent or an oil-based solvent that contains a molecule, an extractant molecule that's been designed to extract the uranium and the plutonium. So our water-based or our nitric acid phase is the yellow in this chart with lots of different elements in it. And the blue is the oil phase with the little moons, which represent the extractant molecule. So they get mixed together. And then because oil and water don't mix you shake it up really vigorously, but then when it's left to settle, the two phases separate out again, kind of like your salad dressing when you mix your oil and vinegar. They do eventually separate out from each other again. And once they separate out, the uranium and the plutonium, which is represented by the little stars, has been extracted by the extractant molecule into the organic phase and into our oil. And the remaining elements are still left behind in the water or the vinegar phase, to continue with the salad dressing analogy. So what can we do with this uranium and plutonium once we've extracted them? Well, they can be made into what's called a mixed oxide or MOX fuel. Mixed oxide because it's a mixture of uranium oxide and plutonium oxide. And by taking the uranium and the plutonium out of used fuel and converting them back into a MOX fuel, we can get more energy from material that otherwise would have been treated as waste. And that can increase the number of years that nuclear power would be a viable option for power generation. So our current fleet of nuclear reactors around the world are not able to use pure MOX fuel. They haven't been designed for MOX fuel. They've been designed usually mostly for uranium oxide fuel. But our current reactors can typically use up to 50% MOX fuel. And there are many designs for future reactors that would be able to run exclusively on MOX fuel. And this is an example of one of those designs, which has MOX fuel with varying amounts of plutonium oxide in it. So beyond recycling of uranium and plutonium, the other three elements that we're really interested in separating and recycling from used nuclear fuel are these minor actinide elements that I mentioned when I was showing you the periodic table. So minor actinides are also very radiotoxic and very long-lived. So it would be great if we could remove them from used nuclear fuel and burn them again in reactors. So the trouble with that is that they're very similar to lanthanide elements, which are also present in used nuclear fuel. And if you have a mixture of the minor actinides and the lanthanides together, then the lanthanides will absorb all of the neutrons and prevent the minor actinides from actually burning as a fuel. So we need to be able to separate the minor actinides from the lanthanides if we're going to actually be able to recycle the minor actinide elements. But it's really difficult to separate them from each other because chemically they're almost identical. So I like to think of this as like identical twins. Your general person on the street cannot tell them apart. It's only someone who knows them really well, like their mum and dad or their sister or their brother, who can actually tell identical twins apart. So it's the same thing with minor actinides and lanthanides. Most organic extractant molecules can't actually tell them apart from each other. You need a really special molecule to actually be able to tell them apart. And there are a few different processes by which we could try and achieve this minor actinide-lanthanide separation. And one example is here where, so first of all, if we had a solution of used nuclear fuel, we would apply the Purex process to separate out the uranium and the plutonium. And then we would have the minor actinides and the lanthanides all together. And then we could, the minor actinides and all the fission products together. And then we could apply a separation of the minor actinides and the lanthanides together, which is not too difficult because they're very chemically similar, and separate the minor actinides and the lanthanides from all the other fission products that are in used nuclear fuel. And then we have a solution that just contains the minor actinides and the lanthanides, which makes it less complex to try and separate those two very chemically similar elements. And the idea then is that we could use generation 4 fast reactors to burn the minor actinides. So currently the reactors that exist around the world are what we call generation 3, but there are lots of designs and ideas about ways that we could build advanced generation 4 reactors. And some of those include what are called fast reactors, which are able to burn more of the uranium-238 that's in nuclear fuel, and also they would be able to burn the minor actinide elements. There aren't any generation 4 reactors that are operating on a large scale, but there have been experimental and demonstration fast reactors that have been built around the world in countries like Russia, India, China, and Japan. And this is an example of one in Japan. So if we go back briefly to our Purex process, I talked about how we have an extractant molecule that does the that pulls the uranium and the plutonium out of the acid phase into the oil-based phase. And in the Purex process, that molecule is this one that I've drawn down here, which is called tributyl phosphate, or TBP. And it's a really good extractant molecule because it is pretty simple and easy and cheap to make, but also because it's pretty stable, which it needs to be because it has to handle some quite tough conditions. So as I mentioned, used nuclear fuel is typically dissolved in nitric acid in order to do this kind of separation and recycling. So the extractant molecule needs to be acid stable. It also needs to be radiation stable because obviously there's plenty of radiation flying around in this process. So this tributyl phosphate molecule is very acid stable. It does a great job in that respect, but it's not that radiation tolerant. So once it's been used a few times, it does start to degrade. And you then end up with, and the organic solvent that it's in also does degrade over time. So by doing the Purex process or any solvent extraction process on a radioactive material, you end up with an organic solvent and an organic molecule that are degraded that you eventually have to replace. And so you're creating a secondary waste stream in the process of trying to deal with your first waste stream. And so that's one of the big disadvantages of solvent extraction as a process. And in order to address that, my research in particular is interested in, can we use solid phase materials to achieve these kinds of separations rather than using liquid-liquid or solvent extraction processes to achieve these separations. So how that would work is you have your solid material, you put it in a column like this, and you simply flow through the solution of used nuclear fuel dissolved up in nitric acid, and you've designed that material to be selective for one particular element, in this case the blue element, so that that blue element sticks to the solid, but all the other elements flow straight through. And the advantage of this is, as I said, you don't have an organic solvent that you end up with as a secondary waste stream, because in an ideal situation, you would then be able to directly convert that solid material that's been loaded up with your uranium, for example, into a matrix fuel or a transmutation matrix. So you'd be able to directly put it back into a reactor to burn. So the challenge when we're trying to design these kinds of solid phase materials to do separations is just like in solvent extraction, they need to be stable, both to acid and to radiation and to temperature to a certain extent as well. They need to be selective because they need to be able to pull out one or two elements when there are, maybe 50 elements present in solution, and they need to be like, no, I don't want that element. I don't want that one. I'm just going to pick up this one. And we also want them to be porous because a higher porosity or an open structure in our material is going to give us a higher surface area and a higher capacity for the element that we're trying to separate out. So I'm going to move into talking about my research a little bit more now. Basically, in my research, a lot of what I've done is I've looked at extractant molecules that other people have developed for solvent extraction, and I've tweaked them a little bit to try to incorporate them into a solid phase material to achieve the same kind of separation that they can achieve in solvent extraction or in liquid-liquid extraction, but to try and get it to work with a solid phase material. So these two molecules are like the mum and dad, I guess, of the minor actinides and lanthanides that can actually tell them apart, tell the identical twins apart. So these are two molecules that have been developed over many, many years of research into trying to achieve that minor actinide-lanthanide separation for a solvent extraction process. So the one on the left was for a process called selective actinide extraction, or SANEX, was developed in France, and the one on the right was developed for a process called all-sep actinide-lanthanide separation. It was developed in the US. And these are kind of the best that anyone has been able to come up with so far in terms of being able to tell apart the minor actinides from the lanthanides. So I've basically looked at them. I've based my work largely on the molecule on the left, the BT-Fen molecule, and put similar structures, made molecules with similar structures and put them inside of solid phase materials. In this instance that I'm first going to talk about, putting them on the surface of titania or titanium dioxide. So I've used titania because it's very stable, both to acid and to radiation. And then, as I said, coated the surface of that titania with an organic molecule that has a similar structure to that BT-Fen molecule that we know is able to tell apart the minor actinides and the lanthanides. And I did this both on titania beads, like you can see here, and also on just titania particles to see whether it actually made a difference if we had a better or a higher surface area, more porous structure that we were using. So when we just use the titania particles coated in that, that organic molecule, we see that there, and we try to use that material to extract both minor actinides. In this case, we're using americium, AM, and lanthanides. In this case, we're using europium or EU. Then we see that 20%, about 20% of the americium is extracted and none of the europium is extracted using this material. So it is selective for the minor actinides over the lanthanides, which is great. And it took about 2 hours for that reaction to be complete. When we did the same thing but using these porous titania beads coated in the same molecule, we doubled the amount of the minor actinide that we were extracting, and we still saw essentially zero extraction of the lanthanide europium. And it was also much faster. The reaction was complete within about half an hour rather than 2 hours because of that nice open structure in the titania beads. So that was really promising, but we're still seeing quite low extraction in terms of, 20–40% of the americium being extracted. And the concentrations I've used in these experiments are low too. So the next thing I tried was rather than, first of all, making a titania framework and then coating it with the organic ligand, I then went to what's called a one-pot synthesis. So this is just like cooking, the kind of cooking that I love, where you put everything in one pot and you stick it in the oven and you only have to wash up one item at the end of the evening. So it's the same idea. You put all of your reagents into one reactor vessel, you put it in the oven for 24 hours, which is probably a bit long for cooking, but it works in chemistry. And then you pull it out and you have a white powder that's formed, which is kind of like an interconnected gel of, in this case, we're using zirconia rather than titania. It's the same idea. It's a very stable, zirconia is very stable to acid and radiation. And it's formed an interconnected network of the zirconium and the organic molecule. So we can incorporate a lot more of our organic molecule into the solid phase material by using this one-pot synthesis method. And that means that we were hoping we were going to get a much higher capacity for the minor actinides. And indeed, that was the case. So when we did experiments looking at how this material can extract both, again, americium and europium as our minor actinide and our lanthanide, when we have a 1-to-1 ratio of the americium to the europium, we saw that there was 99% extraction of americium and 94% extraction of europium. So much higher extraction of americium, but it's not quite as selective as it was before. But we are still seeing preferential extraction of the americium over the europium. And we can quantify that with something that's called a separation factor and say it's got a separation factor of about 7. We also did experiments with these materials where we looked at, can this material selectively pull out the americium even when there's a lot more europium in solution than there is the americium. So a ratio of 1-to-40 of americium to europium. So even when, as I've tried to show in this picture here, where the purple dots are the americium, even when there's a lot more americium, a lot more europium around, the molecule will still prefer to bind to the americium, the one red molecule atom, because it's still got a higher extraction of the americium, 99% than the europium at 97%. And I am getting pretty close to time, so I'm just going to swiftly go through the last couple of slides, where I just wanted to make the point that about some more recent work I've been doing, which has been about improving the stability of these materials. So as I mentioned, these materials need to work under quite harsh conditions of acidity, temperature, and radiation. So it's really important that the materials are able to withstand those conditions. And I've been looking at how can I synthesize or tweak the conditions in which I'm making these materials to make them more stable. So I can play with things like the pH or the reagents that I'm using to try and make them more stable. So I've done some work looking at temperature and acidity, and some other work looking at radiation with zirconium phosphonate materials. And the take-home message from this is the bonds that form between the zirconium, the oxygen, and phosphorus, those bonds are really strong, and they can withstand acid, temperature, and radiation. So I want to basically create conditions when I'm making these materials to maximize the number of zirconium, oxygen, phosphorus bonds that I'm making, and that will make materials that are really stable and hardy. So to sum up, I guess the take-home message from today is that used nuclear fuel still contains a lot of elements, the actinide elements, uranium, plutonium, and minor actinides, and they have the potential to be recycled and used again as nuclear fuel. The benefits of this kind of recycling is that we can reduce the volume, the radiotoxicity, and the lifetime of the waste that then requires long-term storage and disposal, and create a more sustainable nuclear fuel cycle. And these kinds of actinide separations can be done by solvent extraction and by using solid phase materials. And I want to finish by thanking Women in Nuclear for inviting me to speak today, my colleagues at ANSTO at University of Sydney, University of New South Wales, and CNEA Argentina, who have collaborated with me on this work. And if anyone is too nervous to ask a question today, please don't be, but you can always contact me after the talk as well. So thank you.
Thank you so much, Jess. That was awesome. And I love how you used the analogy of doing a one pot cooking of materials. That's some pretty fun science there to see what happens, right? We have a heap of questions coming through. I'm just going to... do
you want me to stop sharing?
Yes, please. That'd be great.
Stop sharing.
This one on.
Awesome.
All right, before we dive into the questions, I'd like to introduce our two panelists joining Dr. Jess today. So we've got Cecilia Tran and Jim Scott. Cecilia is the manager of the technical team for the Australian Radioactive Waste Agency. And she is responsible for the technical work program, including regulatory approvals, facility design development, the Common National Inventory of Radioactive Waste, and the development of the waste acceptance criteria. She's been involved in the project since 2018, including a role in strategic policy. Prior to her work with the ARWA, she was responsible for the infrastructure policy and other matters within the Office of Northern Australia. And we also have Jim. Jim is the Chief Regulatory Officer at the Australian Radiation Protection and Nuclear Safety Agency. As the Chief Regulatory Officer, he is responsible for the licensing and compliance monitoring for all Australian Commonwealth Government uses of radiation. Jim has worked in a variety of roles, and prior to joining ARPANSA in 2005, he has worked as a medical physicist in the UK, Canada, and Australia. Jim gained significant experience in radioactive waste management during his career in the UK nuclear industry, and has been a member of the Nuclear Energy Agency Radioactive Waste Committee and Regulators Forum since 2006. More recently, he has been responsible for the regulatory oversight of the Commonwealth Radioactive Waste Management Facilities operated by Defence, CSIRO, ANSTO, and other licence holders. So Cecilia and Jim, welcome. We'll get the three of you to answer a heap of questions that have come through. I'll just stop sharing my screen so we can look at everyone's faces. So the first question that's come through is answering, well, where does Australia currently hold its radioactive waste? And Dr. Jess has spoken to us about how we can reduce potential length of time it's held for. What's currently going on in Australia?
Do you want to take that one, Jim, or would you like me to? Oh, you're on mute.
Sorry, I just wasn't sure who was going to take it, but I can obviously shed some light on that. In fact, as you're probably aware, it depends on the waste. You know, waste that's arisen from the nuclear fuel cycle is almost predominantly, in fact, stored at Lucas Heights at the ANSTO site, which has been operating since the mid-1950s. It's had some critical assemblies and research reactors, the wastewater reactor, which has now been decommissioned, a high-fire reactor, which operated from mid-1950 to 2007, when basically the Opal reactor started operating. Well, it actually started operating in 2006. So most of the nuclear waste, as we would call it, which is waste that has arisen from the nuclear fuel cycle, is in fact located at Lucas Heights. There are small amounts, maybe in academia and other areas where small amounts of research have been happening. CSIRO, for example, has undertaken studies looking at other cycles for thorium fuel cycles, as has ANSTO in the past, where there was a lot of excitement in the world about not just uranium reactors. Thorium reactors have actually got some great benefits. So I think that answers the nuclear waste. Radioactive waste is in many locations across Australia. I mean, there are industries such as the mineral sands industries, and also obviously nuclear medicine, and I'm a former nuclear medicine physicist. Obviously, it's a very commonly used radioisotopes used in hospitals for diagnostic imaging studies, and they are in fact manufactured at Lucas Heights also from the Opal reactor and the ANM facility, but they're also imported from overseas, from France, South Africa, and other. So the waste from these is at various locations throughout Australia, but I will emphasise that the intermediate level waste, which is the waste that needs to be disposed of at depths below, tens of meters, hundreds of meters, is almost exclusively located at Lucas Heights. Most of the ILW is with ANSTO. So that's probably the best I can answer that question.
Thanks, Jim. The next question that I think is quite interesting is, what's special about uranium and plutonium that makes them easier to separate than other actinides?
Okay, it's a chemistry question. So in every element in the periodic table has got what's called a valence state, which has to do with its charge when it's dissolved up in solution. So basically, uranium, when it's dissolved up in solution, is usually present as a UO2 kind of uranium with two oxygens attached to it, which is called a uranyl cation. It's got a charge of 2+. And plutonium is usually present as plutonium 4+. So, and all those minor actinides have got a charge of 3+. And all the lanthanide elements also have a charge of 3+. So it's the fact that the minor actinides and the lanthanides are a similar size, and they have a similar charge that makes them really hard to separate from each other. The uranium is present with it's a different size. It's got some oxygen atoms attached to it, and it's got a different charge, and the plutonium does as well, which makes them more different chemically to everything else that's there, and therefore easier to separate out. Does that kind of make sense?
Yeah, that completely makes sense.
Yeah.
A little bit of chemistry for a Wednesday night, hey?
Yeah. I need like a board to start drawing things on when people ask me this question.
The next question is, are there any nuclear proliferation issues created with the separation of actinides?
Yeah, does someone else want, Cecilia, are you good at this question?
Look, I think from an Australian Radioactive Waste Agency perspective, we'd obviously have to defer to ANSTO as the key regulator in that respect. So yeah, look, I can't really answer it, but I don't know whether, Jim, you've got anything you can add?
Yeah, I'll give an attempt. Obviously, any process extracts fissile material has the potential for proliferation. So I guess that if you're extracting or recovering fissile materials in a process such as this, which Jess is proposing, then I guess it does have some potential proliferation issues if that material can be diverted, I guess. I mean, I'll leave that to Jess perhaps to take from there, because the whole idea is that you're recovering it so you can reuse it. So by reusing it, you would want to be using it in the fuel cycle, i.e. for charging a nuclear reactor, but obviously there is the diversion potential.
Yeah, and that is a concern that like one of the arguments for an open fuel cycle rather than a closed fuel cycle is the potential for proliferation. There are ways, of course, in which we could try to minimize that risk. For example, there's rather than a Purex, there's another option, another proposed separation called the COEX process, where the uranium and the plutonium are extracted together and they're never actually separated from each other at any point in the process. Which means that the plutonium which is the highest proliferation risk, is never isolated, and therefore by keeping the uranium and the plutonium together at all times, it reduces the proliferation risk, for example. But yes, you would absolutely want to have very strict regulatory controls in place with this sort of process to make sure that no material is being diverted.
Yeah. I'm really interested in that plutonium-uranium combo. That sounds like a really interesting form of fuel there. The next question is, will the separated waste be suitable for Synrock? And for those that don't know, Synrock is an ANSTO designed way to deal with liquid waste.
Yeah, so I'm not a waste form expert, but I can give my high level understanding, which is the idea with Synrock is that it would be able to be used to immobilize waste without having to do any treatment prior. But for example, it is the case that the things like the actinides, the uranium and the plutonium minor actinides, they go more readily into a waste form like a ceramic, whereas the other fission products that are in used nuclear fuel are more readily incorporated into a glass type waste form. So Synrock incorporates both glass and ceramic, or it can do. But, for example, I can imagine that if you wanted to do this kind of recycling process and recycle your actinides, and then you could use Synrock as a waste form for the remaining fission products and wrap them up in a glass waste form and have something that was really stable. But I guess the beauty of Synrock is that it's meant to be tailorable, so it depends on what waste stream you've got. You can come up with a formulation that's going to work well for whatever waste stream you've got, to a certain extent.
Yeah. So Cecilia, I might ask you then, so what are the waste forms that the Australian Radioactive Waste Agency is looking to accept radioactive waste in?
Yeah, so at this point, we've got a generic waste acceptance criteria, which we've worked really closely with ANSTO and their experts to develop. At the moment, we're working towards a site-specific waste acceptance criteria, which will look at the various forms of I guess, waste storage and disposal, and working towards that. Obviously, coupled with that, we're in the process of also updating our common national inventory on radioactive waste, which will then obviously inform the waste acceptance criteria at the moment as well. So look, it's all very sort of, I guess, at this stage, you know, an iterative process that we're working towards once we get to an operational facility. But we've had some really good engagement with states and territories, and also the Commonwealth Waste Holders to look at that. Obviously, Synrock, TN81, CAS as well is all part of that mix in terms of what we will eventually store at the facility and also dispose of as well.
Yeah, cool. Our next question is, what will be required to convert the output from the process you're talking about, Jess, into a MOX fuel?
Sorry, I better unmute myself. So yeah, I guess I showed that in that diagram, how you extract the uranium and the plutonium into that like organic solvent or oil-based phase. So then you have to strip it back out of that phase. So you would use another water-based solvent to strip the uranium. Well, actually, first of all, there's a reducing agent added to the organic phase, which makes the plutonium-4 become plutonium-3. That's changing that charge and the oxidation state of the plutonium. And that makes it possible to strip the plutonium out first, and then you can strip the uranium out second using a different reagent. And that's where the separation of the uranium and the plutonium actually happens in the Purex process, which is the difference from the COEX process I was talking about before. But yeah, so you have to strip the uranium and the plutonium out of the organic phase, and then they're, yeah, in a probably, I don't actually know exactly what the reagents are that they use, but probably dilute acid rather than concentrated acid would cause that to come out. And then basically you just drying that in a calciner or something to form the oxide and mixing them back together.
All right, we've got another question that, and I'll go out for opinions here. Do you think that in the long term, most countries will adopt a closed nuclear fuel cycle with full actinide recycling?
Tough. I don't know. I don't think all countries will. I think that that some countries will. I think it's probably economies of scale. So countries that have a lot of nuclear power, maybe it makes more sense. And countries that don't have a lot of, natural resources, it makes more sense. And I think that, as time goes on and technology improves, it will become more economically viable. But there are other sources of uranium that people are looking into as well. Like there's lots of research happening into, can we extract uranium out of seawater, for example? So it's really anyone's guess what will end up being the most viable source of nuclear fuel in the future. Yeah, I hope that it becomes, recycling becomes more viable, because it just, from a sustainability perspective, I think it makes a lot of sense. But the economics always win the day.
Well, this one is for Cecilia and Jim. Will the National Radioactive Waste Management Facility end up accepting low-level waste, such as cobalt 57 and cesium 137?
Do you want me to start, Jim?
Yes, go ahead, Jess. Sorry, Jess, Cecilia. I'll come after you. I've got a couple of comments to make on that question, actually.
So I guess in short, yes is the plan. That's sort of what we're trying to learn through updating our common national inventory. It's probably more likely it'll be more for storage than disposal, depending on the levels as well. And obviously through our PANSA regulatory processes too, we'll have to make sure that we meet the safety cases and have plans in place as well to make sure they're disposed of or stored appropriately as well.
Okay, actually, so I'm looking at that question. It's interesting. Cobalt 57 and cesium 137 are actually interesting because they're quite commonly used in medical facilities. The cobalt 57 being a technetium 99M lookalike, and for a short half-life, from my recollection, of about, I can't recall, 270 days or something like that. Now, what the NRWMF will be a low-level waste disposal facility with a near-surface disposal facility, and then a potential storage facility. And it may be that some very short, low level waste can actually be disposed of. For example, the cobalt 57s, once it's stored, can decay to quite an extensive extent because of the short half-life. Cesium 137 is more unlikely. That's more likely to be stored because of its 30-year half-life, and that's probably more for intermediate depth disposal or borehole disposal, is what is the current thinking within the Australian radioactive waste community, that borehole disposal could be suitable for these types of sealed sources. But of course, this will all depend on the design of the NRWMF. We don't really know until we know what the design of that looks like, and then the waste packages that can be accepted, as Cecilia mentioned earlier on, there'll be waste acceptance criteria, and if they can meet the waste acceptance criteria, they can be disposed of.
All right. The next is two questions that I'm going to merge together. When we talk about solvent extraction and the solid state material extraction, are the waste products there able to be recycled, or is this going to increase the types of radioactive waste that need to be managed?
So the idea with so I guess, yeah, there are two ways of thinking about how we could use solid phase materials for separations. One would be that, you use your solid phase material for separations, you've got it loaded up with a minor actinide or uranium or whatever it is, and you could then just simply, so another reason that the materials that I've developed are based on titania or zirconia is you could then just simply apply heat or thermally treat those materials, which would burn off the organic component and create what is already a waste form or an inert matrix fuel that you could put directly back into a reactor to burn the minor actinides, for example. So you wouldn't have to do a lot more processing, and you wouldn't end up with a whole bunch of other wastes that you're generating along the way. The other option is that we could also recycle our solid phase materials. So yes, just like in solvent extraction, how you would strip the uranium and plutonium back out of the organic phase in the Purex process, we could then strip, for example, a minor actinide back off a solid phase material and reuse that solid phase material to do the separation again. So there are kind of two options, I guess, for how you could use your solid phase material. Or you could, I guess, in theory, you could even combine them. You could, recycle your solid phase material until it's kind of not working as well anymore, and then use it as a transmutation matrix. But that doesn't actually work because you've stripped a whole bunch off, which forget that as an idea. But I'm thinking off the top of my head here. But yeah, there are two options for how you could do it. But certainly the idea is that you end up with less waste, less secondary waste generated by using a solid phase material. But yes, by doing a separation process, you do end up with more streams, I guess, in terms of you have, one stream that's got the uranium and plutonium in it, one stream that's got minor actinides and lanthanides in it, and another stream that's got fission products in it, for example. So if it wouldn't really make sense if you were going to turn all of those into a waste form, to do that kind of separation and then turn them all into a waste form. It only really makes sense if you want to reuse or recycle some of those materials, some of those elements that you're trying to separate out.
Okay. We've only got a few minutes left, and because WIN Australia is all about promoting young people to have fulfilling careers in nuclear and radiological science, thought I'd ask each of you how you got into nuclear waste or radioactive waste, so you can outline to each of our members interesting ways they can have those sort of careers. So I might start with you, Jess, and then we'll go Cecilia and Jim.
Yeah, so I'll be quick because I kind of talked a little bit about it at the start of my talk. But yeah, basically, I had no idea what I wanted to do with myself when I got to the end of my university degree. So I started a grad program. And yeah, I worked in lots of different areas from biology to physics, and convinced myself that yes, chemistry, which is where I had started, is actually where my heart lies. Yeah, I think I just, I guess nuclear waste was an issue that I can definitely understand why people have concerns about it. It does last a really long time, and you know, radiation can be a bit scary because you can't see it. And I think that, well, like anything, there's more that we can do to improve our ability to deal with it. So I certainly had no idea that recycling of nuclear waste was even an option. And when I kind of discovered that, I was like, oh, that's really cool. And that's something that I'm interested in working on, and hopefully coming up with some ideas that can improve our ability to treat waste in the future.
I guess from my perspective, the thing that attracted me to work in this field was very much the strong women that I saw working, particularly in this radioactive waste agency. I saw some really strong women who I thought I could learn a lot from, and I kind of, I guess by accident, really enjoyed engaging with the science and dealing with some really great people from ANSTO, Panzer as well. And I feel like I can really add value in terms of trying to translate the tech and the science into something that government can understand, and to influence government, and really kind of get them to understand the purpose and the value of a national radioactive waste management facility, and the way that it sort of contributes to the whole life cycle for nuclear waste as well. So from my perspective, I kind of fell into it a little bit, I guess. But I found it a really interesting field, and really curious about learning the different aspects, but also working with some really fantastic, strong female leaders and some really great people around the industry as well.
And Jim, did you want to share with us how you got into the field?
Just quickly, of course. Sorry, can you hear me? Yeah. Oh, well, I guess I fell into it too. I joined the UK nuclear industry and the generators, and quite quickly found myself dealing with lots of waste, fuel and waste from our power plants, and managing that waste, including storage. I mean, obviously there was no disposal pathway, but obviously the pointy end is in the nuclear industry, where you have spent fuel and irradiated fuel to manage once it's been irradiated in the reactor. So I guess it just came naturally by joining the industry. And obviously when I came to Australia, it interested me that I could participate in the Australian nuclear industry, so to speak, albeit much smaller, but that's how I came to arrive at waste.
Thank you. That's three completely different pathways into a pretty interesting space. So I'll just share my screen with everybody. Unfortunately, we've run out of time tonight. Apologies to those whose questions we didn't answer. We will try and get those answers to you. A warm thank you to Jessica, Cecilia and Jim for taking the time tonight to help us understand the challenges with radioactive waste and how research is looking at helping us recycle it. And thank you to you, our audience, for joining us. I hope you were able to learn as much on some of the amazing research happening out there as I have. If you have any other questions, feel free to reach out to us via our social media or email, and we'll send them through to the appropriate expert to answer. We're also keen for you to keep the conversation going. Our Twitter and Facebook handles are up on the screen. And we also value your feedback. If there is any topic in the nuclear or radiological fields that you would like us to try and pull together a webinar, just drop us a line and let us know. Final thanks to our sponsors and to all our members for coming and joining us this evening. So have a great night.